Hello friends, welcome to our YouTube channel. Two-port networks may be described in various ways. Today we shall learn how to describe two-port networks using open circuit impedance parameters or simply Z parameters. We shall learn how to draw the equivalent circuit of a two-port network using Z parameters. We shall also learn how to determine these parameters. Finally, we shall solve a couple of numerical problems to learn how to determine Z parameters for given two-port networks. An electrical network having one input port and one output port is known as two-port network. Here we can see the block diagram of a two-port network. By analogy with transmission networks, one of the ports is called input port and the other is termed as the output port. Each port contains two terminals, one for the entry and other for the exit. By definition of the port, current at the entry terminal of a port must be equal to that of the exit terminal. A two-port network deals with four variables V1 and I1 for input port and V2 and I2 for the output port. Only two of these four variables are independent. Therefore, any two variables can be expressed in terms of the other two. We use two linear equations to relate these variables. Open circuit impedance parameters represent the relation between the port voltages and port currents in the two-port network. That is, we express the input and output port voltages V1 and V2 in terms of input and output port currents I1 and I2. The linear equations used in this case are V1 equals to Z11 I1 plus Z12 I2, V2 equals to Z21 I1 plus Z22 I2. These two equations can be written in matrix form as follows. Matrix of V1, V2 equals to matrix of Z11, Z12, Z21, Z22 into matrix of I1, I2. Or simply we can write matrix of V equals to matrix of Z into matrix of I. The elements of matrix Z are known as Z parameters. These parameters are determined performing open circuit tests. That is why they are known as open circuit impedance parameters. They are measured in ohm. Now let us draw the equivalent circuit using Z parameters. The linear equation used to describe a two-port network using Z parameters are V1 equals to Z11 I1 plus Z12 I2 and V2 equals to Z21 I1 plus Z22 I2. We have to implement these two equations while drawing the equivalent circuit. Let us draw the input and output ports first. And now let us assign the port voltages and currents. If we examine the first equation, we see it contains two parts. First part Z11 I1 can easily be implemented by connecting an impedance Z11 at the input port. The second part Z12 I2 is nothing but a dependent voltage source controlled by the output port current I2. So let us draw a dependent voltage source Z12 I2. Now let us examine the second equation. It again contains two parts. The second part Z22 I2 can easily be implemented by connecting an impedance Z22 at the output port. The first part, Z21I1, is nothing but a dependent voltage source controlled by the input port current I1. So let us draw a dependent voltage source Z21I1. That is the equivalent circuit we obtained using Z parameters. Hope you will now be able to draw the equivalent circuit using Z parameters. Now let us determine the Z parameters. First, we shall connect a voltage source at the input port and we will keep the output port open circuited. Therefore, I2 equals to 0. Now let us connect an ammeter at the input port to measure current I1 and let us connect two voltmeters to measure port voltages V1 and V2. The linear equations we have used to describe our two-port network using Z parameters are V1 equals to Z11I1 plus Z12I2 and V2 equals to Z21I1 plus Z22I2. When I2 equals to 0, the first equation reduces to V1 equals to Z11I1. Therefore, we get Z11 equals to V1 by I1. Z11 is termed as driving point impedance at port 1 or open circuit input impedance. When I2 equals to 0, the second equation reduces to V2 equals to Z21I1. Therefore, we get Z21 equals to V2 by I1. Z21 is termed as forward transfer impedance. Both Z11 and Z21 are measured in ohm. Let us determine other two parameters Z12 and Z22. For this, we will connect a voltage source at the output port and we will keep the input port open circuited. So I1 equals to 0. Let us connect an ammeter to measure the output port current I2 and two voltmeters to measure the port voltages. The linear equations we use to describe our two-port network using Z parameters are V1 equals to Z11I1 plus Z12I2 and V2 equals to Z21I1 plus Z22I2. When I1 is 0, the first equation reduces to V1 equals to Z12I2. Therefore, we get Z12 equals to V1 by I2. Z12 is termed as reverse transfer impedance. When I1 equals to 0, the second equation reduces to V2 equals to Z22I2. Therefore, we get Z22 equals to V2 by I2. Z22 is termed as driving point impedance at port 2, or it is called open circuit output impedance. Both Z12 and Z22 are measured in ohm. Let us solve a couple of numerical problems. First, we shall find Z parameters for the T network shown. Let the input and output port voltages be V1 and V2 and the loop currents are I1 and I2. Applying Kirchhoff's voltage law, we can write from loop 1 V1 equals to ZA plus ZC into I1 plus ZC into I2. From loop 2 we can write V2 equals to ZC I1 plus ZB plus ZC into I2. The linear equations we used to describe a two-port network using Z parameters are V1 equals to Z11 I1 plus Z12 I2 and V2 equals to Z21 I1 plus Z22 I2. Comparing these two sets of equations, we get Z11 equals to ZA plus ZC, Z12 equals to Z21, that is equal to ZC, Z22 equals to ZB plus ZC. Let us find Z parameters for the resistive T network shown. We have found that for any generalized T network comprising of ZA, ZB, ZC, Z11 equals to ZA plus ZC, Z12 equals to Z21 equals to ZC, Z22 equals to ZB plus ZC. If we compare these two networks, we find ZA equals to 20 ohm, ZB equals to 30 ohm, ZC equals to 40 ohm. So we can write Z11 equals to ZA plus ZC, that is equal to 20 plus 40 equals to 60 ohm. Z12 equals to Z21 equals to ZC, that is equal to 40 ohm. Z22 equals to ZB plus ZC, that is equal to 30 plus 40 equals to 70 ohm. Let us find Z parameters for the AC T network shown. We have found for any generalized T network comprising of ZA, ZB and ZC, Z11 equals to ZA plus ZC, Z12 equals to Z21 equals to ZC, Z22 equals to ZB plus ZC. Comparing these two networks, we can write ZA equals to J20 ohm, ZB equals to 10 ohm, ZC equals to minus J10 ohm. Therefore, we get Z11 equals to ZA plus ZC equals to J20 minus J10, that is equal to J10 ohm. Z12 equals to Z21 equals to ZC equals to minus J10 ohm. Z22 equals to ZB plus ZC, that is equal to 10 minus J10 ohm. We have to find out Z parameters for the resistive network shown. This problem can be solved in various ways. First, we shall use delta star conversion technique. We shall take out the delta comprising of 2 ohm, 4 ohm and 2 ohm. If we convert it into star, we get RA equals to 0.5 ohm, RB equals to 1 ohm and RC equals to 1 ohm. Let us put this star back into the network. So it becomes like this. So it looks like a resistive T network. If we compare it with generalized T network, then we get ZA equals to 1 ohm, ZB equals to 1 ohm and ZC equals to 3 plus 0.5, that is equal to 3.5 ohm. Therefore, Z11 equals to ZA plus ZC equals to 1 plus 3.5, that is equal to 4.5 ohm. Z12 equals to Z21 equals to ZC, that is equal to 3.5 ohm. Z22 equals to ZB plus ZC, that is equal to 1 plus 3.5, that is equal to 4.5 ohms. Now we shall solve this problem using mesh analysis method. Let the input and output port voltages be V1 and V2 and the mesh currents be I1, I2 and I3. Applying Kirchhoff's voltage law, from mesh 1 we get V1 equals to 5I1 plus 3I2 minus 2I3. From mesh 2 we get V2 equals to 3I1 plus 5I2 plus 2I3. And from mesh 3 we get 0 equals to minus 2I1 plus 2I2 plus 8I3. Therefore, we get I3 equals to I1 minus I2 divided by 4. By using this expression of I3 in equation 1, we get V1 equals to 4.5 I1 plus 3.5 I2, and from equation 2 we get V2 equals to 3.5 I1 plus 4.5 I2. The linear equation used to describe a two-port network using Z parameters are V1 equals to Z11 I1 plus Z12 I2 and V2 equals to Z21 I1 plus Z22 I2. Comparing these two sets of equations, we get Z11 equals to 4.5 ohm, Z12 equals to Z21 equals to 3.5 ohm and Z22 equals to 4.5 ohm. So, today we have learned how to describe a two-port network using Z parameters. How to draw the equivalent circuit using Z parameters. how to determine these parameters, performing open circuit tests at input and output ports. Finally, we have solved a couple of numerical problems to determine Z parameters for given electrical networks. That's all I have for you today. Hope this lecture has been useful for you. If you have any question or suggestion, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.